Welcome friends, Igor is here, and in this video we will see that linear independence guarantees uniqueness of the vector representations by linear combinations. In this lesson we will learn that every vector in a given vector space can be expressed as a unique linear combination of the vectors in the spanning set as long as that spanning set is linearly independent. Let's get started. I'm going to introduce this new idea gently by first looking at a specific example. Let's consider the following set of three vectors in the vector space C3. We can construct a matrix A by using these column vectors as columns in the matrix, and we can easily check that this is a non-singular matrix because its reduced row echelon form is the identity matrix. Because the matrix A is non-singular, its columns, which are the vectors in the set S, are linearly independent. Therefore, S is a linearly independent set of vectors in C3. Let's take an arbitrary vector B in C3. Then we can construct a linear system with A as the coefficient matrix and this vector B as a vector of constants. This linear system has a unique solution because its coefficient matrix is non-singular. This means that the given vector B can be expressed as a linear combination of the columns of the coefficient matrix, which are vectors in the set S, in only one way. Of course, in particular, because it can be represented as a linear combination, this vector B belongs to the span of the set S. The vector B was chosen arbitrarily, so this argument works for every vector B in the vector space C3, and this proves that the set S spans C3. But in fact, we proved more than that. Not only did we show that every vector in C3 is a linear combination of the vectors in S, we proved that every vector in C3 is a unique linear combination of the vectors in S. Let me illustrate this observation by fixing a particular vector B. The linear system AX equals B has a unique solution because A is the coefficient matrix, and you can use any method you like to solve the linear system. For example, you can reduce the augmented matrix, or you can find the inverse of the coefficient matrix. But in any case, you will arrive to the same unique solution to this linear system. This unique solution can be used to construct a linear combination of the columns of the coefficient matrix, which is equal to the given vector of constants. Moreover, the solution is unique. This means that this linear combination is also unique. And what guaranteed this uniqueness was the fact that the set S was linearly independent. So, given a vector B, there is a unique set of three scalars which represents this vector B relative to the linearly independent set S. Now, we are ready for the general statement that if you have a spanning set that is also linearly independent, then every vector can be expressed as a linear combination in a unique way. Intuitionally, for now, you can think of a linearly independent spanning set as the optimal, minimal spanning set. It contains just enough information to construct all other vectors in the set, and it does not contain any excess baggage. Let's state and prove the main result of this video. Suppose we have a vector space V, and we have a set B of vectors in this vector space, which is linearly independent and spans the vector space. The title of the result mentions the word basis, and we will discover in the next video that basis is precisely a linearly independent spanning set for a vector space. Back to the statement. If we take any vector W in the vector space V, then this vector can be expressed as a unique linear combination of the vectors in a given set B. The fact that any vector W in the vector space V can be expressed as some linear combination of the vectors in B follows from the assumption that B is the spanning set for the vector space. The real question here is this: is there more than one way to represent this vector W as a linear combination of vectors in the set B? We will prove that the given presentation is the only presentation. There are no other such linear combinations possible. Remember our pattern of how to prove that an object with certain properties is unique? We are going to assume that W can be expressed as two linear combinations, and then we will prove that these linear combinations are in fact the same. Namely, we will prove that the lists of scalars are in fact identical lists. To do this, let's subtract the second equation from the first equation. On the left-hand side, we have vector W minus vector W. This is the zero vector. And on the right-hand side, we subtracted the linear combination using B scalars from the linear combination using A scalars. Next, we use the commutative property of vector addition to rearrange the terms, and then the distributive property to simplify the expression. But what we got here is a relation of linear dependence on the set B. We assumed that the set B is linearly independent. Therefore, the only relation of linear dependence on this set is the trivial relation. This means every scalar in this linear combination must be equal to 0. A1 minus B1 is 0, A2 minus B2 is 0, and so on. But these equations actually say that A scalars are the same as B scalars, and this completes the proof of the fact that this linear combination presentation for W is unique. If you found this video helpful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will define the super important notion of a basis of a vector space. I will see you later.